programming. So it's great to have her here.
Okay, so galaxy morphology, which is like classification of galaxies and food for black holes.
So what are galaxies? Well, galaxies are large systems of stars, gas, and dust that are held together by gravity. And in each of these galaxies, there contains a very large amount of stars. The average is about 200 billion stars per galaxy. And there are two types of galaxies, elliptical and spiral. These are the only two common types. And most big galaxies host supermassive black holes.
Okay, so one type of galaxies is spiral galaxy. An example of a spiral galaxy would be like our Milky Way. In a spiral galaxy, they have relatively flat, like disk, and they have a bulge in the center. And they also have spiraling arms moving outward where most of the stars exist. In spiral galaxies, they are relatively more young and contain more gases that make them more hot and brighter and blue than elliptical galaxies.
So elliptical galaxies they're older and they're more red because they're not as hot stars in them, and they don't have as much gas or anything in them. So they are known as dead galaxies because they don't have any more gas to form for new star formation. Some scientists believe that they are as a result from merging galaxies. And so elliptical galaxies appear as like a bulge they usually appear as a bulge that's about the shape as a football, and they look smooth and they don't have any disk or arms like a spiral galaxy does.
So what are AGN? Well, first of all, most large galaxies host supermassive black holes. And of these black holes, only 1% of them are AGN, which stand for active galactic nuclei. And AGN basically means that these black holes emit enormous amounts of energy. Our Milky Way has a black hole, but it is not an AGN.
Okay, so we came up with many hypotheses. Our first hypothesis is how, since we know spiral galaxies are more young and they contain more gases than elliptical, we assume that they would have AGN black holes because with all these gases, they would feed these AGNs. And that's why we expect for the spiral galaxies to have these AGNs.
Our second hypothesis has to do with how we find these AGN. So because there's a lot of gas and dust separating us from the black holes, it's hard for us sometimes to see the black holes. So we think that X-rays and gamma rays, which is beyond our light spectrum, are going to work better for finding these galaxies because they can go straight through all that gas and dust.
Our third hypothesis is that more blue galaxies will host AGN. And blue galaxies are mainly spiral galaxies. They have much younger stars, and because they have younger stars, they have more gas to form more stars, and this gas is used to power the AGN.
So our last hypothesis is based off of galaxies that are merging together. In merging galaxies, it causes them to stir and a chaotic event where a bunch of things fly around everywhere.
So when galaxies merge, it may cause the black holes to become active because when all that gas is moving around colliding, it may cross the event horizon of that black hole, therefore triggering the black hole and turning it into an AGN black hole.
So these are our procedures. First, we had to make the questions to classify each of the galaxies. So we had 5 questions in all. So the first question is whether the galaxy is an elliptical, spiral, or an artifact. The second question is how edge-on it is. So this was rated on a range of 1 through 5. So 5 is the most edge on, so it would appear almost as a straight line. And 1 is, it would appear as a complete circle. The third question is how blue or red it is, and this is also rated on a range of 1 through 5. So 5 is the most red, meaning that it is the coolest, and 1 is the most blue, meaning that it is the hottest. The fourth question is whether the galaxy was a merger, disturbed, or neither of these. And the last question is whether it had a dust lane.
Then we had to get the images that we were going to apply these questions to and classify them. So we had to obtain sample images, and we got 3 selections. One was out of gamma rays, which is like the beyond our visual light spectrum, detecting rays that are coming out of the black holes. Then there is optical AGN. So these are like what we can see, and they all have AGN in them. And the normal are optical images that certainly do not have AGN in them.
Okay, so after that, we will classify all these images with the questions that we said above.
Then, after classifying the images, we calculated their standard deviation to see how reliable the data was, and then we found the percentage of each of the classifications.
So after saying all those questions, you might have been wondering what all those were. Well, if you look at this, here would be an example of 2 merging galaxies. This would be like an elliptical galaxy. It's more smooth than these 2 spiral galaxies. And here's an example of an edge on both of these. They look like a flat line relatively and a bulge in the center. And also, if you look closely, you can see a dark brown floating material here. This is a dust lane. And finally, in this image here, this is an example of an artifact. And an artifact is where like there are stars or a bunch of image objects in the sky that are like obscuring our vision of these galaxies.
So the selections that we made were very specific, so they had certain terms that they had to get across. So first of all, our galaxies were all at the same brightness and redshift, which is basically distance, so we could take out all those other variables. All our images were from Kit Peak and the SDSS, which is a Sloan Digital Sky Survey. The optical AGN were found using spectroscopy and high ionization levels, and the normal galaxies have no AGN from optical spectroscopy.
Okay, after in our procedure, we mentioned standard deviation. Standard deviation is where it tells us how reliable our data is based off of the mean and how much it increases or decreases. In the standard deviation, here's the formula for standard deviation. S would represent that, which is equal to this letter here, E, would be like the value of an object. That would be like a value we would input for X. Like for example, we mentioned like we would rate a galaxy on how edge on it is between 1 and 5, say 5 for example. We'll put 5 here on X, and this would be minus by the mean of this here, of all the data received for that category, and we would square that divided by n, which is the total number of like images we looked at, minus 1 and square root.
So these are our results. So n is the mean, which is the total number of galaxies in each section. The sections are normal, optical, and gamma rays. For elliptical and spiral, these are the total number of galaxies that we classified as elliptical and spiral in each of the sections and the percentages of the total. For edge on and color, that is the standard deviation. So the first number you see is the mean plus or minus the standard deviation that you get. For artifacts, again, that is the total number of galaxies that we got from each section, and for merger, dust lane, and disturbed, those are also the total number of galaxies that we obtained in each section.
So the first conclusion we came to was that spiral galaxies host more AGN. So in the gamma rays, we can see that the spiral galaxies has a 53% compared to the 47% of elliptical galaxies. So this shows that there are more spiral galaxies hosting AGN. And while in normal, where they had no AGN, they were 100% elliptical and 0 spiral. So this also helps our case because most elliptical galaxies host no AGN. And for the optical, we're not very sure where this data comes from because we don't really know for sure, but we think it might be because of the gas and dust obscuring our vision that we might not be able to see it clearly. So the optical kind of sets us off, but because it's 2 to 1, we are going to go with spiral galaxies.
So we also thought that edge-on galaxies would have more gas and dust because there is more gas and dust interference in optical than in gamma rays because gamma rays can penetrate through gas and dust. But as you can see in our data, for the edge-on, all of the standard deviations were consistent. There wasn't really a significant difference in each of them. So the variability was pretty much the same for each one. So the hypothesis could not be supported with our data, but it cannot refute it either.
Okay, so earlier we talked about how blue galaxies would host more AGN because of how there's more gases to create these blue galaxies. And in our data, we found out that there are more, we rated the galaxies for 1 through 5, where 1 would be blue. And in the gamma ray, since we know they are just these AGN galaxies, you can see how the 2.6 here refers more to the 1 of blue than in normal, where there are no AGNs, which is more closer to the red side of 5.
So our last conclusion is about merging galaxies, and we concluded that they do in fact have more AGN. So as you can see here, in the gamma rays where they're all AGN, we can see that there are much more merging galaxies than where there are no AGN. So this leads us to believe that merging galaxies do in fact have a significant impact on AGN and in galaxies.
So future work. So when we classify these galaxies, we basically use our human eye. But to improve the accuracy, because we may have different ways of classifying it, we could use computer programming to make the data more reliable. We could also need a larger data sample of galaxies, because in our project we use 330 galaxies, but a larger data sample may make the data more reliable. We could also obtain more recent images of galaxies because in our project, the images were from a while ago. We would also like to use different telescopes such as the Fox telescope, and we would also like to classify the galaxies with other features other than the 5 that we formulated.
Like, since the only telescopes that we used were the Swift satellite, which was a multi-wavelength observatory, and another one we used was the SDSS, or Sloan Digital Sky Survey, that used only red, green, blue, infrared, or ultraviolet filters. And the other links are to help us classify.
We'd like to give a special thanks to Mr. Koss for mentoring us about galaxy and everyone from High Star for the support and help.